Okay, thank you, Paul. So many of you here are, I imagine, chip designers or system designers, and would like to give you just quick snapshot, very quick highlights of what are specific advantages of FDSOI technologies you can think of to make difference at your level, either device level or system level. And Paul mentioned talk about this equation between cost and performance, but as you will see, there are a few other critical aspects where FDSOI can bring huge differentiation to your product. And again, it will be very quick. There's a lot of data available, and we'll be happy to share it with you. There's a lot of public references, so if you need details, we can share it with you very, very easily. So just first a list of the key things which are unique for FDSOI, and I will go to after that to probably one slide for each as an example. So first one, this body bias. Paul mentioned about body bias. So with FDSOI and only with FDSOI, you can design your chip in the way that then in your device you can, from at software level, you can use the same transistor either at very low leakage or very high performance, and you can move it from one state to another depending what application you're using and what function you're using. And think about mobile applications. Think about IoT. It's just perfect feature for this type of applications. I come back to this. Second one, faster processing. ARM demonstrated that with FDSOI and body bias, you actually can perform as well or even slightly better than FinFET. So this is not the technology to compete with FinFET, as Paul explained, but in some extreme cases when you need to do so, you can do it with FDSOI. Next point is very low, ultra low power performance, and this is quite amazing thing that you can operate a device built on FDSOI at 0.4 volt. 0.4 volt. It's huge. It's for IoT applications. This can be really something which will just a game changer. So today people are starting to design with this feature. RF performance. I was talking before about front-end module, but now if you're talking about the transceiver, the baseband, FDSOI can provide Fmax at least two times higher than any other technology. So when you're going towards 5G, and we'll show some details, this is the technology which can bring very, very differentiated performance. So this is again another feature which is differentiating this technology and can be very unique for you. Reliability. This is, again, core value of SOI in general, but even more amplified on FDSOI, fully depleted type of substrate, where soft error is significantly lower than bulk or any 3D structure. So this, for many applications in the past, it could be military or satellites, but now in automotive industry, this type of feature becoming a huge differentiated in the chip design. And finally, link limits to RF performance, analog performance, also much better on FDSOI than any other technology. So you see here, this picture, just a big snapshot of what FDSOI can bring as differentiation to your design, at device level or then at system level. And these topics are today in the first adoption of this technology on the market. They are, depending. I will show a few examples, and Lode already mentioned about one. These are, motivation for people to use FDSOI. And if you want to bring something, quickly on the market using planar technology, which is FDSOI, this is way to go, because you have very low risk and you can provide very differentiated performance. So first, just 2 words about each of these key features. So body bias. So it's quite amazing thing to do, because with FDSOI technology, you can really have, through software control, use body bias, either with reverse body biasing, so with very, reducing to strict minimum leakage, or you can do forward body biasing and then boost performance. And depending how, so you can have here, a lot of economy, power economy, energy economy, so sleep mode for some applications. And here, when you need a lot of computing or data transmission, you can boost performance. So very, very unique feature, only available, with FDSOI technology, perfectly suitable for many of the upcoming IoT applications. And people are starting now to design using this feature. Here you see, it's maybe hard to see from back of the room, but again, we can share the data later on. You see here, there's 28 high-K metal gate technology, and here's 22 FDSOI technology. So already, as Paul mentioned, you can gain 40% in performance, or you can gain 50% in less power consumption at equivalent cost for 28 nanometer. So this is what technology brings on its own. Once you apply body biasing, you can boost it further on. You see here that you're adding another 50% of, from this point, you can reduce 50% power consumption, or you can boost performance by another 30%. So FDSOI plus body biasing make a huge differentiation in terms of what you can provide in terms of behavior of your chip, depending on what application you are using. And there's a lot of data available, and first, real chips on the market available. Here is the case of when you can use FDSOI technology in high performance mode. Again, it's not to compete with FinFET, very different applications. But you can see here that this data is coming from ARM, that FDSOI can provide equivalent performance at same cost as or lower cost than FinFET. So it's, again, you as a designer may think about that as opportunity, because it shows how much flexibility is with this technology. So this is another amazing point about FDSOI is performance at 0.4 volt. And here you have the data from Global Foundries. Now they are demonstrating the first chips are already reaching this type of working point today on the market. So 0.4 volt, again, for IoT mobile applications, very unique value you can get. 5G applications. So all this is coming up, but again, you probably don't see here. You have various applications from cellular to Wi-Fi to different modes for 5G to satellite communication radar. So you have frequency in gigahertz going from over about 2 gigahertz to almost 100. You have this 3x, 5x. What is typical way you define your design window, and very clearly only FDSOI can cover the full range of these requirements. FinFET can do some of that, but FDSOI today is the one which is going farther into the spectrum of all these 5G new applications. And from what we know and cannot really disclose in detail, several key companies, fabless companies, who are today setting up 5G applications and chips, they are already designing an FDSOI just because of this value, this specific capability of FDSOI to handle these very high frequencies. There's a lot of value in analog performance. Again, we'll be happy to share the data with you. So you see here, the difference between 25 low power high-K metal gate and 28 fully depleted SOI, and there's the big jump in the performance for analog applications. So perfectly suitable for something which hasn't been done today. And it's, for people who have been using much bigger design rules, this is giving opportunity for future generations of products to move to technology which is, cheaper, lower performance, lower power consumption, and better analog performance. I think there's one missing here, but anyway, probably maybe it will be later on. So here's a few examples, concrete examples of chips already on the market or being announced publicly by some companies. Here you have GPS built on FDSOI, 28 nanometer FDSOI, and it's now in the smartwatch. The brand is Wami. It's a part of Xiaomi in Chinese brand. And this chip built by Sony on technology from ST Microelectronics provides extremely better performance in terms of battery lifetime. And this is exactly what is FDSOI about, that you can get, same performance or better performance at significantly reduced power consumption. And here you see, I think you should see it, all these, blue bars here are all the smartwatches available on the market. There you have them, Garmin's, Apple's, and other brands. And the numbers here, or the size of the bar, is showing numbers autonomy in hours for the smartwatch using GPS. GPS very, very hungry in power consumption. And then the last bar in red here, it's the battery life on this smartwatch using GPS built on FDSOI. So you can see that there's roughly five times better performance, longer performance of GPS built on FDSOI than on standard bulk technology. So this is the first consumer product on the market showing the value of FDSOI. This one of this, this fraction of the value, because I show you many other elements which are not used here in this example, in this chip. And this is, you can imagine, and we working with Sony, who is one of our partners. This is changing completely the game. Having a GPS which can perform 5 times and soon maybe 10 times longer than before. It's changing completely the way you're using GPS in applications. From the smartphone you have, where GPS is by default set off because of power consumption, you can imagine that it will be set on all the time because there's so many new applications can be built on it, and nobody will worry about power consumption anymore because it will consume 5 or 10 times less than equivalent GPS chip available today till now. So a big game changer. And the price, and it's cheaper. It's cheaper than what today some of the reference chip makers have been providing on 28 nanometer high K metal gate bulk. Another adopter of FDSOI technology is NXP, and before that was Freescale. So names probably So 2 generations of products. The family is called IMX7 and IMX8, built for various applications from IoT to industrial to automotive. And again, we'll be happy to share all the data available. You see here their decision matrix, how to choose between bulk technology, high-K metal gate, FDSOI, and FinFET for their specific applications. And the key criteria were energy efficiency, cost competitiveness, ease of design, and ease of diversification. So how you can reuse the same platform for different applications. And the winner was FDSOI. And you see here the value for this here specific chip design for leakage, dynamic power, and area. And it was a winner. And today, this chip is showing up on the market in some very, very disruptive consumer applications we can't name today, but you will see soon, it will be very, very obvious. And it's also going to automotive market. Talking about automotive applications, there's this couple of features which are making it, FDSOI extremely attractive for these applications. And, here example is Mobileye, and maybe many of you know about Mobileye, this Israeli company, one of the leader for ADAS applications and computing. There's actually a couple of things here worth to mention. So some of the applications require computing, or like, for example, car camera based built into the windshield, so on the glass. So this can work only if the power consumption of this processor is very low. Otherwise, heat is too much on the glass, and the chip will not function. So there is a limit that this chip can consume not more than 3 watts, and but still deliver a lot of the performance. So you see here that this 5-watt chip was a no-go. There wasn't a solution for this application. With FDSOI 28 nanometer, which is performing at 3 watt, it's opening the door to this specific application. So it's a game changer because of the power consumption for this specific image processing application. The second one I mentioned already is soft error. So because of all different type of impact from radiation, different type of radiations coming from the engine, from electrical engine or other type of radiation. Today in the design, often you need to design having additional chip or additional capability just to prevent that there is a soft error in the calculation. With FDSOI having a major, significantly lower soft error, you don't need to worry to have this additional capacity of the calculation, or this double circuit, just in case of the error. You can design in simpler mode, and you can see here that you don't need to have redundancy on the chip. So you gain in the cost because your chip is smaller, it's simpler. So this is another key value of FDSOI now being used by car makers, and this is one of the biggest opening for FDSOI beyond IoT, beyond mobility, is this topic. So I won't repeat everything I said before, but specifically if we go to IoT, there's a lot of the value proposition of FDSOI is huge through energy efficiency, through power performance trade-off, so body bias, integration of RF and analog features, and the cost efficiency. A lot of data, the value proposition is very strong, so keep it in mind. Just few words also as a reference point from design standpoint. Just we stay on the core part, which is coming from bulk. So I think Paul mentioned about it earlier. So majority of elements of the design are exactly the same on the bulk, with some features, of course, like body bias, which require some additional things. But overall, it's a continuity rather than disruption when you go to the FinFET. And from the IP and design standpoint, this work in progress, but the ecosystem is getting reinforced every day more and more. And here are a few examples. GlobalFoundries set up very strong ecosystem and growing to support all the design on FDSOI. So this is getting really very strong. You see here some of the examples. Here is Synopsys, but same with Cadence. About their support for FDSOI. Here is just again snapshot of from Samsung of design IP support covering all the critical blocks and growing. Same from GlobalFoundries. So all this ecosystem to be able to to build chips, to design chips are, getting in place. Most of them are already in place. So for you, if you have ideas how to that you actually would like to use some of these very unique features of FDSOI, it's time to go. And this is overall ecosystem. So from from all the R&D part to substrate like Soitec and our licensees to IP and EDA tools to foundries and the major foundries, just to repeat, Global Foundry and Samsung, but also ST Micro and Renesas, and then all the IP services community. This is the ecosystem which is today in place, and you guys can play a very big role in using it or being part of this ecosystem, because FDSOI is becoming as a standard for all the reasons we mentioned today. Why they are becoming technology which will taking very, very big place on the market in coming years. And maybe Paul, the last slide you summarize.
Yeah, the wrap up is clearly. I think that what you have in front of you is clearly the opportunity to decide in terms of what market you want to get into, what technology you want to get into, and what partnership you want to get into. But I think it's the success of your success is really belongs to this type of decisions that you will have to make. Clearly, what we believe today is that the future of semiconductor in India is linked to creative partnerships and local entrepreneurships. It's clearly, the mix of these two that will create the speed and also the value that you are looking for. We are offering that value to you in terms of with IMEC today and with Soitec. We are clearly trying to give you a snapshot of what can be done on a very specific type of markets. There is many others, but it's all about what you want to do and at the speed you want to do it. And clearly, we can, with IMEC, we can really bring this expertise and the network to bring your idea at the level it is today from just an idea to reality. We can access and partner with you from very early design standpoint into prototyping and making a chips and the testing and go to a pilot and go to manufacturing. So wherever you are in the process with IMEC, clearly we have this capability here to drive you or to help you to go faster and to change the rules. Okay, because that's exactly what you need to do. We didn't mention too much about China here, but China started to adopt FDSOI. They looked at this 2 years ago, they believed in it, and they have started to build this infrastructure right now to accelerate and really to become a player. India is the same. I think this is an opportunity not to go through the entire full process, but you have to make the right choice for the right product and for the market you want to serve. So with this, I think that we want to really thank you for hosting us today, for your attention during this 1 hour and a half, and we are open to questions. Clearly, if you have questions, please, we are all here to engage with you. So the first question is always the most difficult one. Here it is.
So thanks, Paul and Thomas. I have, in fact, 4 questions. One thing Thomas has clearly taken up for, I think for any of the technology, we'll be needing the IPs or foundation blocks. I think for 28 he has shown something, but is it for every technology like 22 or something, all the IP or foundation blocks are available?
So today, majority of IP libraries are available for both nodes, 28 nanometer supported by Samsung and ST Micro, and 22 nanometer supported by GlobalFoundries. Still work in progress, as I said earlier, but it's very dynamic, very quick progress to get it ready, and a lot of effort from these foundries and their partners to enable to catch all this wave of IoTs and small companies and startups. So not just focus on the big ones who can afford developing something on their own, but also helping enabling small customers.
Thank you. One more thing which you mentioned is a tool set. So definitely when we use the FinFET tool set, yes, definitely there are features which requires a lot special licenses. So what about using this technology, FDSOI? Does it require some special licenses, or with a normal bulk CMOS, technologies we are using it? With same tool set we can go ahead.
No, you can approach especially well, all three foundry partners available on today, ST Micro, Samsung, and GlobalFoundries. They are fully independent, and they have all the tools and IP available to to support.
No, sorry, my question was something else. From the tool set point of view, EDA tool set point of view. So, if
no,
we have,
there's nothing different, nothing specific.
Okay, so whatever with the planner, CMOS,
yes,
whatever we are using,
absolutely.
There's no specific special license
no.
which is required. Okay, fine. You have also covered manufacturing. This thing, I think 3 sites you have already shown. What about the wafer facility? You have at one location only, or for wafer also you have 3 different, at least?
So for FDSOI,
yes.
Soitec today has one facility in France.
Okay.
Another one will be starting soon in Singapore. Fab is already existing, and depending on the demand, we have also plans for another location. We also have, as Paul mentioned, 2 licensees. So 2 other companies, one Japanese, Shinetsu, who is leader in silicon bulk, and one US Taiwanese, Sun Edison, which is now Global Wafer, who has also facilities in the United States. So the ecosystem and supply from the substrate standpoint point of view is in place to support multi-million wafer demand.
Thank you. Thanks.
I am from a university, Amrita University. I don't see any partnership from the academic institutes. Do you also emphasize anything? Is there any role for us to play in this?
Well, there's a lot of collaboration with academia, with Berkeley, with Stanford, with Tokyo University, with UCL in Leuven, and then really the 2 key partners we have, maybe step up is IMEC and CA Leti. But yeah, a lot of collaborations with universities and research centers.
So if I want to suppose look at that opportunity, whom should I contact, or how should I proceed?
You can go through us. You can go directly through IMEC, through the people here today. I mean, this is one of us will drive you to the, and we can have a discussions and bring you to the right next step.
So yes, on the if there is an interest, we can really help and discuss actually the area where you would like to engage, and then see what is like the best partner to do that. But no problem, yeah, sure, we can exchange contacts.
So, this is the main reason is about parasitic capacitance linked to three dimensional structure. So this is making the biggest difference in terms of impact on Fmax between comparing to FinFET and then also to standard bulk technology. And this is being now being, as I said, adopted by some of the key players who already designing with FDSOI technology, reaching this 5G performance at very different applications. Yes, yes, that's correct. Yeah. So there's, especially Global Foundries has very elaborated offer related to RF performance and analog performance on FDSOI. They have work package related to this. It's public information. It's available. I can provide you the link to all this information. They're actually doing some of this design in India, and this is it's very powerful, very unique offer on the market. Yes. I believe so. Yeah.
Hi, can I ask a question? Well, actually, when I raised my hands, I wanted to ask the same question actually that Professor Murthy. So, I am a volunteer in the IESA Talent SIG, the Talent Common Interest Group. So, as Professor Murthy also was mentioning, if you can tie up with, you mentioned 200 odd colleges, you have connections. I don't know how many of them are Indian universities. So, if you can also do an inroad with an active program to roll out this technology through colleges, that will slowly rub on to the companies as well. So now coming to my main question. So from what this is a generic technology question. So from what I understand, at some stage in the semiconductor history, so industry, Intel took the FinFET path and some other people took the FDSOI path, right? So in retrospect, after some more years, is Intel also coming back into SOI? Have they made any announcements towards that effect so that they can have both the twin lines of FinFET and SOI? I don't know.
So it's a very good question. It goes back that it's not two technology that will compete against. In fact, it's a market decisions. So Intel, and I'm not Intel, so don't quote me on this. But what I think Intel will do, if they want to go IoT, if they want to go on wearables, they cannot use the same technology as the one they are pushing for very high performance, very high technology. They will have to think through a different model. And that's what, for example, I mean, some of the guys like Sony are doing. Sony can push one technology for high performance, and they will use FinFET for the high-end microcontroller, microprocessor, and they will go FDSOI for the GPS.
Maybe indeed. We are working with all these companies already for 10 to 15 years. And actually we had more than 15 years ago, we already had a FinFET program. Like even in the late 98, 99, I make it early. This was all on SOI. We developed the whole FinFET on SOI. Only the industry those days wanted to have a solution in bulk. Right? Today, if you compare the data with a fin in bulk, of course, which is more leaky by definition than an SOI solution. So that's the history. And I think those companies, for the high performance market and the most advanced scaling, for them it made very much sense to go for this high density scaling. In terms of area saving, area scaling, and having the ability to put more on the same die, in terms of area, I think for them it made sense to go 3D in a sense, right? And then squeeze this fin more and more. And that's what's now happening in like the 7 and the 5 nanometer. Of course, if you want to do that, you also need to an interconnect which goes along with it, and a whole patterning chain. You want to do the patterning of your gate, you need to do the patterning in the interconnect. It becomes quite expensive. Everyone knows. It was mentioned that EUV, although we are in IMEC a strong defender of EUV and I think also enabler all through the years. And that technology is today at the verge of being there. However, we are 2017, right? So EUV has been delayed a long time, and you have a lot of multiple patterning steps have been developed, which have increased the number of masks significantly, right? So that, of course, is introduced also in the cost picture for those nodes. Certain steps are combined with design trade-offs, like combined with the patterning solutions. So yes, it made sense for them to squeeze too thin because they needed the last nanometer in area. They still need it. And this was said earlier in the presentation. For a number of chips where you still need that last piece, right? People will still move for that. But there are so many applications. And definitely not all of these applications will need that final area saving and also volume, right? Because there is a lot of investment also in terms of design verification, modeling, as was said. So that's where actually the message is the technologies are next to each other available to serve the most appropriate application. It's on itself a little bit a study, I think, to see where you park your design and what is best for you. But there are definitely many areas out there which are clearly demonstrated in the examples by Thomas, where you have the benefit of the FDSOI.
Thank you.
I'd like to add, to everything Lode said, specifically about Intel, and please do not quote me, but Intel is the biggest adopter of silicon photonics as they are leader in data center, and SOI, they're using it, in production today for several years. Same for RF applications. This is a standard. Intel is using it. So depending, as Lode said earlier, depending on application, you need to pick up the right technology to that.
Well, thanks, guys. So this is a very educative session. So just if I extend this question, which path did IBM take? I mean, the last big foundry player. So the IBM. I mean, what is the strategy of IBM?
The IBM microprocessor roadmap is following the FinFET route because they have to deliver like the Intel. They have to compete with the today the 16, 14 nanometer, and tomorrow with the 7 nanometer. So they are on this competing route, which is the very high performance. Now, the ASICs from IBM, I don't know, they may decide to take another route as this kind of technology is built. So again, it's more the opportunity that Ajit wanted us to share with you is that there is alternatives. There is alternatives route, and the complexity of this industry and the cost associated to it is one thing. And we need all together to think smart. We need to think smart. And depending on what you want to achieve, look at this Xiaomi watch. They pick the GPS on the shelf from Sony. They put it in a watch. The watch itself, the price of the watch is $130 US. Look at the competitions. The competition is in the $400 US, the Garmin watch. And we didn't even put the Apple Watch because GPS on the Apple Watch is not even on the screen. Okay, so if you want to have a successful design on the market, you need to integrate what you want to achieve and pick the right technology. And there is alternatives, and it's a race, but it's not a race just to compete. It's also a race to change the game. Ajit? The wafer manufacturing at the end, 22 nanometer. What Global Foundry is saying is that they are going to sell you a 22 nanometer wafer, fully processed, okay, at the cost of 28 nanometer bulk, with the performance of a 16 FinFET. Okay, so this is the way that Global Foundry positioned the cost or the pricing today. And now, if you look at the die, the chip itself, basically you can think about a 30% saving when you have a chip built on FD versus built on FinFET.
Time for one more question. Yes.
Yeah, there was a slide in there with ENVM in the bubbles. I wanted to know if this technology is suitable for integrating flash storage, or what was the intent of that? Maybe you can.
This is a very important development that is that is happening as we speak from ST Micro, Global Foundry, and Samsung. The three companies are really developing this new embedded flash memory, non-volatile flash memory into the system, different technology that they are going to use. But they need to bring that into the roadmap in order to have, when you think about IoT, memory is part of the die, memory is part of the chip, and this is going to be available next year, I believe, in full manufacturing. But you can still design and work on this. And that will be one of the key advantages also of FDSOI.
On ENVM, a lot of things are happening too, right? Today, you have it available up to 55 or 40 in bulk, and when you move high-K metal gate, like scaling flash to that technology becomes very complicated. Typically, people are struggling. You can find the solution. I think on FDSOI it might be a little bit better. Alternatively, people are also working on like the emerging memory technologies. There's also something where, because in these IoT devices, recently you've seen maybe some announcements, you have resistive RAM that can come in at 40 nanometers. There are companies who have an initial product release for certain products. It fits the requirements. You have STT-MRAM, so magnetic RAM. The additional advantage of these emerging memories is that you can integrate them completely in the backend, right? As embedded memory, you use the transistor of the front end and you put your memory in the backend. So in terms of mask layers, it's quite efficient and cheap. So this is a trend, definitely with a lot of innovation, where, and that can even enter a little bit earlier already, right, to 40, because once you have such a module, you can, and it even a little bit node agnostic, right, because you have it on 40 and it can scale further to 28 or whatever technology you want to put it on. This is the idea of having various functions in the same system. Yeah, so, but definitely also look at these novel memories.
Paul, if there are no other questions, I think Isa has one more ritual to do here. Please come. Rajiv, is that your show here?
Thank you. I think a very informative and very interactive session. And I think it's also a lot of knowledge and learnings. And I'm sure the audience will definitely benefit from this technology or the solutions that are being driven. And we look forward to a more increasing interaction over there. Any more questions? I think I'll request maybe outside the session you can have one-on-one. And we probably now can close the session. And I'll, some Mentos, right? Fine. Thank you. That's it. Thank you very much. And
Dr. Lowers will take the honor.
I take the honor.
He's the one who did the talk. Yes.